Hi everyone, we're back for our very last edition of Quadratics in Quarantine, bonus edition. Today we're going to do a little bit of problem solving, and so a lot of what we've been doing so far with quadratics has sort of been the basics, but of course when in real life we use this to solve problems. So we used back in grade 9 linear relationships, y equals mx plus b, to solve problems. And we did a lot of that at the beginning of this year, where we had two linear equations and we found out where they crossed. If you remember back to the substitution and elimination method, it was all about finding that point of intersection, the solution, and that also became the solution to the problem that we had. So what we're going to do today is I'm going to go through 3 examples of how we can use quadratics to solve a problem, solve for x. So in the first example, and I posted these notes for you. I'm not going to rewrite the questions out, just too time consuming. So I'll sort of do that orally with you right now. But in example number 1 here, it mentions that we have a picture that is 10 centimeters by 5 centimeters. And it's surrounded by a nice mat. That's that colored piece of cardboard. And the width of the mat is to be the same on all sides. And the question asks, what's the area of the mat to be twice the area of the picture? So we want this mat here to be twice the area of the picture. We also know that it's going to be the same on all sides. So this is going to be an x. This is going to be an x. This is the width in all these cases. In all these cases, the width is going to be x. And so we can say that let x be the width of the mat. And of course, anytime you can draw a picture here, a diagram, it helps out. So first of all, the area of the picture. That's easy. Area equals length times width, which is 10 times 5, which is 50. Because the question says that the area of the mat is equal to 2 times the picture, we know that the area of the mat is 100. It's got to be double the picture. So we have a little bit of information to go with here. Now, the mat itself, what is the length of the mat and what is the width of the mat? So the length of the mat here, it's going to be 10 plus 2 x's. Where do I get the 2 x's from? Well, this is 10. There's 1x, there's 2x. So you can see that this distance, 2x's plus 10, gives us the length of the mat. And likewise here, our width of the mat is going to be 1x, 2x, so 2x's plus 5. And of course, I would write this with my variables first. And so there's the length and width of the mat. Now to get the area of the mat, which is what we're trying to find here, the area of the mat is going to be the area of this whole thing minus the whole, right? If we take the whole area and we subtract the whole, we are left with just the mat. So let's do that. Area of the mat is going to be the area of the total shape. I'll put total here. Area of the mat is the area of the total shape minus the area of the whole, which is the same as the area of the picture. Now we know the area of the mat is 100, so let's sub that in. The total area is going to be the length times the width. So the length here is 2x plus 10. The width is 2x plus 5. So that gives us this total area. And we are going to subtract the area of the picture, which we know is 50. And now we can start to solve this. I'm going to FOIL this out. So 2x times 2x is 4x squared. 2x times 5 is plus 10x. 10 times 2x is plus 20x. 10 times 5 is plus 50. And then we have our minus 50. Simplifying, 4x squared plus, I can put those two together, 30x. And 50 minus 50 is 0. It's gone. I'm going to move this 100 to the other side. If I do that, I'm left with a 0 here. And we get 4x squared plus 30x minus 100. So in grade 9 or grade 8, you may have been taught when you take this plus 100 to the other side, it becomes a minus 100. In reality, of course, what we're doing is we're adding the same thing in on both sides. Here I would add in a minus 100. Here I would add in a minus 100. I've not changed this equation because I've done the same thing to the left side and to the right side, so it's kept in balance. Of course, 100 minus 100 is 0. That's where that 0 comes from, and that's why I'm going to explain this to you. And of course, the 100 stays here. And now we have a question here that is factorable, and that's going to help us figure out what x is. When we factor, the first thing we do is we look for greatest common factor. We do have one here. We have 2. So when we divide this up by 2, we end up with 2x squared plus 15x minus 50. Can we factor this out? Absolutely. A is greater than 1, so we're going to decompose this. And if we wanted to man this out, 2 times negative 50 is minus 100. Have to add to 15. And I believe our numbers become 20 and minus 5. These multiply to minus 100 and they add to this. So within our brackets, we get something like that. And put a second set of brackets here. When we divide this up by 2x, we get 2x, x plus 10. And when we divide this up by minus 5, we get minus 5, x plus 10. Two x minus 5 and x plus 10. There we go, factored out in vectored form. And now we want to find out what our x's are. So we know in this case, x plus 10, we can set it to 0. So x is minus 10. We of course knew that already, that this is in factored form. This is a parabola stretched by 2, and it crosses the x-axis here and here. In this case, it crosses at minus 10. And over here, we'll set this to 0 as well. 2x's is equal to 5. X is equal to 5 divided by 2. So x is 2.5. So what we have here is a parabola stretched by 2. It crosses at minus 10 and at 2.5. It looks something like this. The reason this is a parabola is every time our mat gets a little bit wider, the area gets much bigger, and it gets bigger exponentially. So every time we add, say, 1 onto x, it doesn't mean the area gets 1 bigger. The area gets exponentially bigger. So What that means is if I add 1 onto here, the area might get twice as big. If I add 2 on, it might get 10 times as big. If I add another inch on, so x is now 3, it might get 25 times as big. So it's constantly getting bigger and bigger by a larger amount. Now, so what is our x value of our mat? Well, it's right here. We cannot have a negative x value of the mat. We can only have a positive x value. So we know that in order for the mat to have an area twice the size of the picture, its width must be 2.5. So there we've solved that one. A little bit tricky. For all these word problems, the math is not hard. You can all factor. The hardest part is making sense of it and setting the question up properly. Of course, I have the experience to do that. I've done a lot of these questions, and I can only say that through practice, as we discussed at the beginning of the year, the more you practice these questions, the easier they are at solving. And we found that back in the linear relation units back before March break. Then when we started doing some of the word problems, I could see that you were getting better and better quite quickly at them the more we did them, the more we practiced some of those questions. Okay, question number 2. Question number 2, we're going to start with a formula here. My pen is dying. H is equal to -1/2. All right, so this is a formula for gravitational pull. When things are falling, they are falling because gravity is pulling onto them. And so we do have a formula here. A couple things. One, hopefully you can see that this is in standard form. We have a sort of an ax squared plus bx plus c type of situation. Not only that, it's a negative, and because it's gravitational pull and things are falling down, we expect it to be a negative, and it is quadratic. So last year we dealt with a lot of linear equations. Well, things don't fall linearly. So this would be distance and time. So things don't fall at the same rate. Things actually fall like this, quadratically. And of course, there would be the opposite side as well. So if you were to drop something, it starts to fall slowly. And as it continues to fall, it picks up speed. And then it goes faster. And then it goes even faster. In fact, it's going its slowest when it's dropped or starts to fall. And it's going fastest when it hits the ground. Likewise, if this was a ball and I was throwing the ball from here, say up, it's going the fastest out of my hand, and it slows down as gravity is pulling on it to the point where it actually stops, and then it starts to fall again. So that the speed is constantly slowing down or speeding up, in this case, due to gravity, and that's why it becomes a quadratic situation. So this here is the height. Now you're going to be using this a lot in physics in grade 11 and grade 12 for sure. So this is the height. G is the acceleration due to gravity. And we know that when you drop something, it accelerates at a rate of 9.8 meters per second. This V here is velocity. And this 0 here tells us that it's the initial velocity at the start. And this H here is, of course, height. It's different than this height. This is the initial height. Once again. And T we know is time. All right, so I'm not going to rewrite the question out. I have provided you copies of it, but I'll go over it with you. So first of all, part A says, create a quadratic model. Basically, we want a formula. So let's sub what we know into this. Now, in our situation, it gives us a little bit of information. It tells us that the initial velocity is 51 meters per second. Now, the question does say a toy rocket is launched. So when it is launched into the air, it starts out at a velocity of 51 meters per second, and it is launched from a height of 1.3 meters off the ground. So 1.3 is launched upwards, it's going to peak, and it's going to fall back down, and we have a parabola. This 0 will become of interest to us because that's where it lands, and of course we would have another 0 here in negative territory. That's part of the parabola, but we only deal with the solid line part in the positive territories. So let's come up with a quadratic model. So height is equal to negative 1/2. Our gravitational pull is 9.8. Our initial velocity here is 51 meters per second, and our initial height is 1.3. So there we go. There's our quadratic model, or quadratic formula. We can simplify it, of course, by doing this. Negative 1/2 times 9.8 is negative 4.9 t squared plus 51t plus 1.3. And if this was a little bit scary to begin with, now probably it looks a lot more like a quadratic equation to you in standard form. All right, part B says, how long does it take the rocket to fall to ground? So how long until, geez, I can't write today, till rocket hits the ground? All right, so let's use our formula and let's sub in. So our formula here is all right, so when the height is at 0, that's when it's at the ground. So I subbed in 0 for the h. And just a reminder, in standard form, this is our A, this is our B, this is our C. I'm not going to try to factor this. Look at these numbers, 4.9 and 51 and 1.3. Is there a greatest common factor? I don't know. It'd be a pain to try to find it out to some degree. Trying to factor this is difficult. So let's go with our quadratic formula. So in this case, negative b plus or minus b squared minus 4ac all over 2a. Sub in what we know, negative. Our b is 51 plus or minus 51 squared. Oops, that's minus 4 times 4, negative 4.9 times 1.3 all over 2 times negative 4.9. I think that's 2601 plus 2548 all over negative 9.8. All right, so we get down to this. If you skip this step, that is fine. If you just evaluated it all and got down to this, that is cool. So this is our actual root. And of course, it's minus 5 plus or minus this. So we can say minus 5 plus that, or minus 5 minus 2625 for 8 over negative 9.8. So those are our two zeros, our two roots, two places where this parabola would cross the x-axis. Now we want to actually figure out what they are. If I evaluate this one, I end up with t is equal to negative 0.0244. And if I evaluate this one, we get 10.4325. This is our answer. This is not the answer because, one, it's negative. So that's this point back here. And of course, that's a hypothetical point. This is a point that we want, 10 point whatever seconds, 10.4325 seconds after it's launched, it will hit the ground. Okay, part C of this question says, find the times when the rocket is 95.7 meters in the air. So if we go here to 95.7 meters, you can see at two different times it will be at that height. Our job is to figure that out. So when I'm gonna put 95.7 in for the height part of our formula, and equals negative 4.9 t squared plus 51t plus 1.3. If I move this to the other side of the equal sign, I'm left with a 0 over here, and I get minus 4.9 t squared plus 51t plus, now 1.3, when this comes over, it'll become a 95.7. And in fact, that's what we are doing, just as a reminder here. We're putting in a minus 95.7 on both sides of the equal sign. As long as we put it on both sides of the equal sign, this stays in balance. So 95.7 minus 95.7 gives us 0. And over here, 1.3 minus 95.7 leaves me with a minus 94.4. All right. I would like to factor this and put it into factored form because that'll give me my two zeros. We cannot do that. It's too difficult to use that method, so we're going to use our quadratic formula again. It's sort of the one size fits all approach. Not always it'll always work. Not always the best approach. I've shown you other approaches that work very well and are much simpler. But when the question and the numbers are not simple, then we just go to this method. So plugging in our numbers into our formula, and we get negative 51 plus 750.75 over minus 9.8 and minus 51 minus 750.75 over negative 9.8. And if we solve these, so these are the actual roots, if we want the approximate, that would be 2.41 seconds and 8 seconds. So going back here, we know at 2.41 and at 8 seconds, that's when our rocket will be at 95.7 meters above the ground. So that is that. D says, what's the maximum height? So in this case, we're looking for the vertex. Now, a couple different ways we can do it. First of all, we know our vertex is on our axis of symmetry. We know this point, we know this point, so we can add them together, divide by 2, and that gives us the axis of symmetry, or that'll give us our x value. So we can do that. So it crosses over here on one at the x-axis, and it crosses at 10.3 seconds as well. Divide that by 2, and you get 5.2. So the x value here is 5.2. And of course, we can use that to get the height by subbing it in. I also mentioned last day that this part of the quadratic formula, the minus b over 2a, this will give us the axis of symmetry as well. So if we put in minus b is 51 and 2 times negative 4.9, we get negative 51 over negative 9.8. And when you divide that up, you get 5.2. Look at that, same thing. So yet another way of doing this. And so we take that and we sub that back into our equation. So height is equal to minus 4.9. This is time, so we're substituting it in for here, squared, plus 51, 5.2, plus 1.3. Or sorry, it is time. We know at 5.2 seconds, which is our x value, that's when it's at its peak height. So we're substituting it in for the x or for time here. And when we evaluate this, we get 134. So we know that at 5.2 seconds, the height here will be 134 meters above the ground. So that is our vertex. 5.2, 134. Whew, coolio. Lots of work, but I know you can all do the number crunching. The hardest part is literally setting these questions up. So once again, with practice, it becomes a lot easier. Okay, last question. And then we'll call it a day. We'll call it a year. Example number 3. So this talks about a soccer ball being kicked. And so, and I think I'm gonna have to add this in. I'm looking at the rough copy of the notes that I sent to you, and it might not have the equation, but the path of a soccer ball is h is equal to negative 0.1 d plus d plus. So standard form, a squared plus b plus c, bx plus e. Path of a soccer ball being kicked, we would expect it to be like this. So having a negative makes sense. It's a negative parabola. And it tells us here that this is kicked from a height of 0.5. So that's our initial height above the ground. All right, so question A says, how far does it travel? It says horizontally, so that's how far does it travel along the ground. So first of all, let's just picture this. So we have distance, we have height. It's kicked from a height of 0.5, and it goes like this. It does continue into negative territory. However, we're only dealing with the solid line. All right, so how far does it travel? So height is equal to negative 0.1 d squared plus d plus 0.5. This is though when the height is at 0. So let's put this into our quadratic formula. And of course, so this is when the height is at 0, right? We want to find out when the height is at 0, how far it's gone. So of course, our A, our B, which is 1, and our C. Do you want to try to factor that into factored form to get our zeros? I don't. Let's use our quadratic formula. I'm sure you have this memorized by now. You've written it down so many times if you've done your homework. So our B value here is 1, so negative, and we're putting in the 1, of course. 1 squared minus 4, negative 0.1, 0.5, all over 2a. And we get something like this. And so therefore, d is equal to negative 1 plus all that, and negative 1 minus. So those are actual roots. If we evaluate this, we get negative 0.5 and 10.5. Once again, this one here is impossible. That's this point right here, and that's not possible. 10.5 is possible. That's this point right here. These are our two roots, our two zeros, our two places where it crosses the x-axis. So the distance is 10.5. All right, and part B says, basically, how high, distance when ball is 2.6 meters above the ground. So going back here, when it is 2.6 above the ground, it'll be 2.6 meters above the ground at two different points. So this is find the horizontal distance. That's the distance along the horizon. So we want to find this point and this point. All right, so if the height is 2.6, we can sub that into our formula. 2.6 is equal to negative 0.1 d squared plus d plus 0.5. Let's add a minus 2.6 to both sides. We can do that, keeps it equal. 2.6 minus 2.6 is 0. And here, 0.5 minus 2.6 is minus 2.1. Our A, our B, which is 1, and our C. And we're not going to try to factor that out. Numbers are too dirty. Let's use our quadratic formula, plus or minus b squared minus 4ac all over 2a. Our b is 1, so minus 1 plus or minus 1 squared minus 4 times 0.1 times negative 2.1 all over 2 times negative 0.1. We get negative 1 plus or minus, so 1 minus 0.84 leaves us with the root of 0.16, and 2 times negative 0.1 is negative 0.2. So we have here negative 1 plus the root of 16 and negative 1 minus the root of 0.16 over negative 2/10. Actual roots, much more accurate. If we want the approximate roots, we can evaluate these, and we end up with 3, a height of 3, and a height of 7. There we go. 3 and 7. And actually I said height, that is our distance. We substitute in height, we are solving for D here. So D, sorry. My bad. D is equal to 3 and 7. So at 3 meters and 7 meters from where it was kicked, it will be at a height of 2.6. All right, ladies and gentlemen, that is it. We are done. C'est fini. Have a wonderful summer. I don't know how long our EDSB is going to be up. I'm told it might be the entire summer. That being said, things always change. So get these downloaded And I will periodically check Edsby through the summer if you would like to send a message. If not, you have my email in case Edsby's not up and running. All right. We'll talk to you later.